Okay, welcome back everyone. So today I'm actually going to do another physics video. Namely, we're going to cover Newton's second law in polar coordinates. And it's going to be a derivation, in fact. And um, as you might suspect, it's way more complex than Newton's second law in rectangular coordinates. And I'm actually just going to refresh your memory on Newton's second law in rectangular coordinates, just so you get an idea of the simplification and the elegance of Newton's second law in rectangular. And to show Newton's second law in rectangular, let's just start out by defining a force vector. And namely, that force vector is going to be the force in the x direction, so the magnitude of the force in the x direction, I hat plus f sub y, j hat plus f sub z k hat. We also have some r vector representing the position, and that's going to be, we'll say x I hat plus y j hat plus z k hat. Okay, well, let's differentiating this twice will clearly give us the second time derivative, and again I'm using this notation. I think I've already covered this in previous physics video, but the second time derivative, the two dots on the top mean the second time derivative with respect to this vector. So second time derivative is just going to be equal to x double dot I hat plus y double dot j hat plus z double dot k hat. Okay, and again, now we can simply get Newton's second law by multiplying this by m, and component-wise we extrapolate that the force, so this is our force vector, and we have that our force vector is equal to m times our acceleration, which is exactly the second time derivative of position. So we essentially just get that f sub x is equal to m x double dot, f sub y equals m y double dot, and f sub z equals m z double dot. So that's exactly Newton's second law in rectangular. And as you can see, it's symmetrical and nice and simple, and that's why we like rectangular. But a lot of times it's actually more useful to use things like spherical or polar. So that's why we have to use some of these more complicated coordinate systems. So let's get started. So now let's visualize how we actually set up vectors in polar coordinates. So I'll start out by writing a graph. And to be honest, the graph is the most important part of the proof, in my opinion. Anyway, we start out by considering some kind of point here, right? And actually, we'll eventually consider another point here, for example. And we'll leave that up for now. And we have some vector r representing this. And then we also have some unit vectors with magnitude 1, hence the new unit vector. So we'll have r hat, okay? And we can't forget about theta, the angle. And actually this will be just delta theta. And then we'll actually define theta to be, well, theta hat to be this thing here. Okay, theta hat. And, well, essentially, so essentially this is going to be theta, the vector theta. Okay, and this is theta with unit length 1. Okay, and to continue, well, what is our goal? Our goal is to find the second time derivative of r. Again, our position. So that'll give us our acceleration. But how do we do that? And again, we would multiply that by m and get our force. But how do we get that? Well, what exactly is r? Well, we can define r as being, by definition, and it's also easy to show, that it's equal to the magnitude or the length of itself. So its length times its unit vector. So we have, I'll just denote its length by literally r without the little vector symbol on top. So r times r hat. That's how I'll define it. And that's really easy to see. Well, let's take the time derivative of both sides. So we get that r dot is equal to r dot r hat plus r dr hat dt. And the problem is that we don't know what dr hat dt is. We have no clue what it is right now. So we have to calculate that. So in order to do that, well, let's consider these 2 points. So let's consider this at some time t and this at some time t plus delta t. Okay? And let's say, let's just consider, well, this to be our delta r hat, because it goes from our first delta, it goes from our first r hat to our second r hat. So r1 hat, I guess you could say, to r2 hat. So that's that. But how do we approximate that? Well, let's, for small values of theta, we can consider, let me write this down. So for small values of theta, we can consider delta r hat is approximately, we have, well, delta theta, and, well, this is a vector quantity, so we have to have some kind of unit vector here. So this can be approximated to be the magnitude of that, but we need our unit vector to be something like, well, as you can see, if you look at our theta hat, you can imagine as our delta theta approaches 0, this will become closer and closer to delta r hat. So we'll have actually theta hat. And again, this is actually by, this is approximately d theta, right? So there's a lot of approximation here, but then we're about to get equivalence, which is really neat. So this is approximately by chain rule, theta dot this is approximately theta dot theta dot delta t theta hat, right? Because this is approximately like, yeah, it's kind of like the idea of differentials here. So because we can kind of think about this as approximately being delta theta over delta t, right? And the delta t's cancel and we'll get delta theta. So again, that's why it's an approximation. But then when we divide both sides by delta t, we get that delta r hat over delta t is equal to theta dot theta hat. Okay, well, let's take the limit as delta t goes to 0 on both sides. And notice that the definition of a derivative is literally this entire thing as delta t goes to 0. That's exactly what a derivative is of r hat here with respect to time. So in other words, if we take the limit as delta t goes to 0 on both sides, and the reason that's the definition is because we get the 2 points getting closer and closer together, so it becomes the limit as delta t goes to 0, it becomes literally a perfect tangent, which is the derivative. So in other words, if we take the limit, we'll get delta dr hat dt is equal to, and you can think of this limit as already being taken care of. So in other words, we'll get delta theta hat, theta dot theta hat. And this is really important. So now we can plug that back in here. Very neat, right? This is a trick that often is used in mathematics. In kind of physics related things, scenarios, right? So if we plug this in, we'll get that r dot is equal to, vector r dot is equal to r dot r hat plus r theta dot theta hat. So now we need to differentiate again. So that'll give us theta double dot r vector r double dot, and again we need to just chain rule lots of times, and that'll give us, well, r double dot r hat plus, and then directly plugging what we got from here in, we'll get r dot theta hat. okay? And then here we'll have to use product rule 3 times. So that'll give us, well, plus, well, actually it will give us, yeah. So r dot theta hat plus r theta double dot theta hat plus r theta dot, okay, and our last thing is d theta hat dt. Well, we've run into another problem. We get, what is this? So we use a very similar strategy here. So we want to approximate delta theta hat. And we have to kind of use a different visual for this. Now we consider like both of these different theta hats. So this is like theta 1 hat and then theta 2 hat. Okay, and then we can kind of consider them over here, like what's the word? Basically transitioned over here, translated over to the origin, their equivalent. And again, this will be, this is going to be some delta theta, okay? And over here, this little line here is going to be delta theta hat, okay? And actually, how are we going to approximate this? Well, we'll have our r here, which if we move to the origin, will look something like this, right? That's going to be our r hat, some r hat, right? In some direction. And how do we approximate this for small values of, well, delta theta? Well, what we can do is, again, using a similar idea, we'll have that the magnitude of this will be, why am I putting the equal sign? Not becoming an engineer, please. Is approximately, well, we'll have, again, delta theta, but now this time we'll have to have r hat. Okay? Hopefully that's clear, because we actually, I shouldn't mislead you. Notice that this r hat is in this direction, but we need it to be in the negative direction. So we take exactly negative r hat. So negative of r hat. So that will give us negative delta theta r hat. Okay, and using a similar idea, this is approximately, well, theta dot, negative theta dot r hat. Oh wait, sorry. Delta t r hat, and dividing, we get that d theta hat dt is equal to, well, just negative theta dot r hat. Okay, this is our second important result. And finally, we are about to conclude the proof. So plugging that in, we simply get that r double dot is equal to, and let's try to combine things. So, well, where are our hats? We have this term and we have this term. We'll have an r hat, and this term will actually exactly become r. Well, actually, it'll become minus r theta dot squared r hat, if I'm not mistaken. Yes, okay. So plugging this in, again, we get that we have r double dot minus r theta dot squared r hat plus, and now our theta hats are all here. So that'll be, well, that'll be 2 times r dot theta dot plus r theta double dot. Okay, and that's theta hat. And finally, we just essentially multiply everything by m and set that equal to f, and we're done. So I'll write our finalized result, which is exactly that f force is going to be equal to, actually I'll write it in component form. So our force in the r direction is going to be equal to, well, component of r hat is exactly going to be equal to m r double dot minus r theta dot squared. Sorry, I'm missing the m. mr theta dot squared. And then finally f in the theta direction is going to be equal to 2m r dot theta dot plus m r theta double dot. And we are done. There are a few more things I would like to point out about this though. So what do you think actually is theta, the time derivative of theta? Well, hopefully that looks familiar. It's actually angular velocity. So this is often denoted by a lowercase omega. So oftentimes I'll add a note. We have that theta dot, I'll write is congruent to, meaning that it used in the same way as lowercase omega. Not the same thing as w, lowercase w. Furthermore, we have that theta double dot. It directly follows from this that theta double dot is the angular acceleration, so often denoted with alpha, which is fairly intuitive, right? Okay, and a few more things. Well, actually, I would like to point out that I will go into this later in more detail, but we have this weird, strange 2r dot theta dot term. This is actually called the Coriolis Acceleration. And yes, I'm not gonna go over it at the moment, but it is pretty interesting. Anyway, and if you think this looks ugly, actually, there is a simpler way that you can simplify this in certain problems where, for example, if you have a swinging pendulum, that's a common problem where obviously in that case the r vector will be constant. So in other words, if the r vector is constant, the two derivatives of r are exactly going to be 0. So in other words, if r is some c, this term goes away and we're just left with that term, and then here this term goes away. So we're left with some nicer results. Anyway, I hopefully enjoyed this problem, well, this derivation, and most likely in the future I'm going to be actually doing a problem related to that pendulum problem I just described. So hopefully enjoyed and have a nice day. Goodbye.